All right. Okay, if you can see my hand raised, raise your hand. Raise your hand if you can see my hand. All right, now we're going to have to motor through this, so, and I'm not going to be lecturing the whole time, but when I do give some explanation, I want everybody to hear it so we know what we're doing. Samantha is handing around a little sheet of paper. You don't have to hand this in. This is a sheet of paper to help you just kind of grasp 2 or 3 important things that we're going to do here. Protein molecules, I don't have my keys. Someone have a set of keys?
Like car keys?
Like car keys. Okay, we got a fob. Okay, good. Car key. Now that looks a lot like my car key, but I doubt that my car key will start Stephen's car. What?
Doesn't matter. You know it.
Okay, I got us all distracted. The point here is this. Keys have a very specific shape to them, a very particular structure. And that structure is essential to the function of the key. This key is to start a car, a particular car. And Stephen's car will only start with a key with an exact structure like that. Fits in and activates that lock and starts that car. Well, this seems a little pretty fine because, if everybody held up their keys from a distance, you'd say, they all look alike. And actually, if you held up a whole bunch of proteins, you'd say, oh, they look like a glob. They're globular proteins. They just look like an ill-defined shaped glob of something. But that nothing could be further from the truth. Each protein is very finely structured, and that's why we get so much into it right here. And I want you to appreciate what we mean by primary structure, secondary, and tertiary. Every protein molecule will have aspects of those 3 categories of structure. And then only complex proteins that are 2 or more protein molecules have also quaternary structure, 4th level. So let's go through real quickly what is primary, secondary, and tertiary. Primary is the amino acid sequence. So a protein has a particular order of amino acids in it. Starts with a certain amino acid, the very second one is another particular amino acid. That is the primary structure. So we're going to just get some real simple definitions here. So the primary structure is the amino acid sequence. Are you done, Dustin?
I am.
Okay, thank you. Amino acid sequence, and the kind of bonding here, you could either say we got peptide bonds, specifically peptide bonds. They are covalent bonds. A peptide bond is a type of covalent bond, but we've got really a specific connection between the amino acids that's holding this sequence together. So right here, if we just looked at primary structure, we would just be looking at the backbone of the protein molecule. We'd start out with a nitrogen, let's say here, and we'd be working along certain amino acids going on a certain sequence and ending up with a carbon. And that's about what we would have at this point in time, the amino acid sequence. Secondary structure, that strand, that protein strand, can start twisting into 2 particular shapes, either the alpha helix or the beta pleated sheet. And the bonding that's occurring here, remember remember our peptide bond is like this. Here's our peptide bond. Secondary structure, get the alpha helix, beta pleated sheet. I'll show you examples of this real quickly here in a minute. This involves hydrogen bonds, and they are from one of these NH groups to one of these. Not this one to that, but one of these to 4 or 5 amino acids down, about 4 amino acids away. This hydrogen will hydrogen bond with the carbon-oxygen double bond. But what's involved here is the peptide bonds, hydrogen bonding from the NH in the peptide bond to a carbon-oxygen double bond in another peptide bond further along on the protein backbone. All right, so we haven't said anything about R groups yet, but this is secondary structure. So let's take a look. Here's the alpha helix. So if this is our amino acid sequence, this ribbon going up through here, and you've got these little white bars are covalent bonds walking up through the protein backbone. But here is a carbonyl, carbon-oxygen double bond. If I make that any bigger, it starts kind of disappearing. Well, carbon-oxygen double bond here, hydrogen bonding up to an NH, you see, about 4 amino acids away. You're getting this hydrogen bonding. And it's twisting it into a helix and holding it there. These aren't covalent bonds. These aren't as strong as covalent bonds, but there's many of them. Many of these little bonds. I always try to talk about the Lilliputians in Gulliver's Travels, where Gulliver's this big giant, and the giant comes into the land of Lilliputians, the little tiny little Lilliputians, and they're scared of Gulliver, but Gulliver lays down in the field, falls asleep, and they get out their rope, which is kind of like thread, and they bind him down to the ground with all this thread. Each strand of thread is weak, but there's many of them holding that in position. So that alpha helix can flex a little bit. It's not rigid, but it is in an orderly shape. That's the alpha helix. Hair protein forms this. Many protein molecules will have portions of it that are in an alpha helix, but not the whole thing. But hair protein, actually, from beginning to end, is just this alpha helix. And then there are many of these in a hair strand. There might be 50 of these across, making for a pretty strong strand of hair. But this is the way hair protein orients itself. A beta pleated sheet, well, this slide, this is your alpha helix. This is kind of looking down through it, but you can see the R groups are just flared out of the alpha helix. They're not inside, they're sticking out. They're not involved in holding it into the alpha helix, but they are around. We're going to get to the R groups in a minute. Another form of secondary structure is a beta pleated sheet. So if you think of a string and you run the string along and you bend it and you come back right next to the string and next to the string and next to the string, you would have a sort of thing where you might have an NH group here, hydrogen bonding over to a carbon-oxygen double bond over here. So you're getting this NH, there'd be a peptide bond along here. So you got a peptide bond, you're going along your thing and going along your amino acid sequence, protein backbone, and so now you're getting hydrogen bonding going across between the strands, and they're laying more or less flat. That's a beta pleated sheet. Okay, tertiary structure. Tertiary structure. When we talk about tertiary structure, we're talking about R group interactions. And I'll have a slide that kind of goes through a bunch of them, but let me list at least 4 right here, and I'm going to list them from the weakest to the strongest kind of R group interactions. There's hydrophobic,
Strongest to weakest.
the weakest to strongest. So this is the weakest. Polar interactions, salt bridge. I'm going to give you examples of each of these, and a disulfide bridge. All right. This is your tertiary structure, and this is this slide. I really like this slide because on one slide it's showing all of these examples. So let's try to picture what we got here. The ribbon is your protein backbone. So this is your peptide, your polypeptide here. Polypeptide, amino acid, amino acid, amino acid. There might be 500 amino acids in a particular order. Now, why do they have to be in a particular order? They have to be in a particular order because this R group has to be right here so that it can have this kind of an interaction with this R group that is, maybe 100 amino acids later, and you get this interaction. Here's one where you can probably see it. These would be phenylalanines. Can you see that? Phenylalanine. What's the R group? It's a benzene ring. And there's a nonpolar. So here you need a phenylalanine, and along here you need another phenylalanine to get that interaction like that in this protein molecule. So this is highly specific what's going on here. So let's look at the first one, hydrophobic. Alanine and valine up there. I'm not going to label all these, but just so you can see what's going on. We have a particular amino acid with a methyl group on it, as the R group, valine with a isopropyl group, and those are nonpolar groups. And they're hydrophobic. Keep in mind that this is all water here. This thing is embedded in water. The protein is existing in an aqueous environment. So these guys would like to find a non-polar environment. So they create one between them. They're naturally creating a little bit of a hydrophobic environment right there. Same with the phenylalanines here. So these are hydrophobic interactions. Weak, but still an influence, a weak influence. Then now here is like serine. Some of you made serine. It has an OH group on it, polar bond. There might be another serine here, hydrogen bonding to this OH on this serine. That's a stronger interaction. That's a good hydrogen bond between with an OH here, an OH there. This is positive, this is negative. So that's getting stronger. Hydrogen bonding here, like this, hydrogen bonds. Salt bridge. Now this could be a lysine. Now these were 2 on your homework. Lysine, and this would be glutamic acid. Glutamic acid is actually a negatively charged R group. Lysine is a positively charged R group. And like sodium chloride forms a salt, you're going to have an ammonium carboxylate there forming a salt. You got a bona fide positive negative ions attracted to each other. That's pretty strong. And the strongest is where you get 2 cysteines. And you're all going to see this, whether you made a cysteine or not. We're going to be bringing cysteines up here and binding them together into a disulfide bridge. It's a bona fide covalent bond right there. Cysteine to cysteine, and you get a disulfide bridge. I mean, this is like putting staples in 2 sheets of paper. They're stuck together now. You're stapling that. You're stapling it there. Here it's like Post-it notes, okay? Post-it notes. Yeah, it's sticky, it's stuck on there, but you can pull it off and move it around and all that sort of thing. But this here is you're really stapling. You're stapling this protein at that point. All right, so let's look at the disulfide bridge. Here's a cysteine. This ends with a thiol group, an SH group. Another cysteine, SH group. You take 2 hydrogens off of here, and you form a sulfur-sulfur bond. There's your disulfide bridge. I know I'm saying this really fast, but are you catching this? You with me?
Can we go back to 16, chapter 16? I might be like, go. You're good.
Okay. I'm going to miss that guy. For a while. Okay, so this is just mentioning some of those. Okay, just to mention quaternary structure. Simple proteins are going to be defined by their primary, secondary, and tertiary structure, and we're going to end it right there. Simple means a single protein molecule. Hemoglobin is a complex protein made up of 4 protein chains, okay? And those 4 individual units get associated to one another in a particular way. Now, we're not going to go into exactly what that looks like, but just say that that particular way they get associated with, we're starting to talk about quaternary structure. Quaternary structure deals with 2 or more protein molecules. And how they are associated. So 2 or more protein molecules and how they are associated with one another. That's when you start talking about quaternary structure. So you have to be talking about a protein that's made up of 2, 3, 4, 8, 10, 12 protein units. That's quaternary structure. We're not going to deal with that particularly today. We're going to deal with insulin, and everything we do with insulin is going to be at the primary, secondary, tertiary level. So if we had an amino acid sequence, if you had a bunch of amino acids in a certain order, that's your primary structure. If it got into an alpha helix, now you're starting to talk about secondary. When those R groups twist and turn it into a certain configuration because of the R group interactions, now you're at the tertiary structure. And then this would be the hemoglobin example, where you have 4 protein molecules making up hemoglobin. Okay, so now let's move on to our insulin. Just quickly to just look again at the peptide bond. This is what we're going to do. Someone's going to bring from one of your teams. You're going to bring up an amino acid. I'm going to have that person hang on to this nitrogen and just stay there with that nitrogen. The other end of the molecule is going to have a carboxyl group. And we're going to bind that carboxyl to an amine and form a peptide. And form a dipeptide. So you're going to have a nitrogen, a carbon, and you got a dipeptide. Okay, now take a look at this. You're going to see this on the next slide. Cysteine, cysteine, threonine, serine, isoleucine, cysteine. 6 amino acids. I've given you 7. The 7th one will come in a minute. But let me show you where these 6 are. Here is insulin. Cysteine, cysteine, threonine, serine, isoleucine, cysteine. All right, that's 6 of the 7 that you made, and there's the 7th one. So let's take this is human insulin. It's made up of chain A and chain B. This is the amino acid sequence of chain A. This is the amino acid sequence of chain B. And you can see that you need 1, 2, 3, 4, 5, 6, 7 amino acids on chain B. You need a cysteine so that it can bind back to this one. And then you go moving along some more, and you got another cysteine bound to a cysteine. You'll see it in a minute. Here are the 7 that we made. So we're not making insulin, but we're going to make that part of it. Follow me? A big chunk of chain A, and then I just at least want you to see where chain B would be attached to it.
So are the cysteines from chain A and chain B, are they being held by the isomaltone bridges?
Yes, yeah. Yeah, these are going to be actually sulfur-sulfur bonds right here. And even this right here is a sulfur-sulfur bond. They drew a real long line right there just because they had to. They just had to draw that line. But we're gonna bind that. We're gonna have a disulfide bond right there. Now, some of you, all of you could look this up. Don't do it now. You can do it after class. But bovine insulin is just like this, except for one amino acid in here. I don't know if it's this last one or this one, but there's one amino acid difference between human insulin and the insulin extracted from pigs. So 20, 30 years ago, people who were taking insulin, they were actually extracting it from pigs, isolating it, and that's what was being prescribed for people with diabetes. And they would inject that insulin. But 25 years ago or so, I don't know how many years ago, they worked out the way to synthesize this in this amino acid sequence. That's pretty wild chemistry right there.
Putting pig insulin?
Yes, yes. It was the insulin that was about the closest to the human amino acid sequence, and it worked. But the one that is perfectly the human sequence works better, and is accepted by the body better, and all that sort of thing. So more recently now, they're actually taking insulin that is this sequence right here. Okay, so let's piece this together. And then at certain times we'll stop and just kind of try to relate what we're doing back to what we see right there. So we'll leave that up there. And I want someone, 2 people with cysteines to come up here. 2 two teams that have a cysteine.
You want us to bring a molecule?
Yeah, bring your molecule. Okay, just two. Wait one
Whatever,
second.
Steven.
Okay, come on, Stephen. Come on. And Stephen, you're going to be my anchor right here. Stand, turn this way, turn towards me. Hang on to that nitrogen. So this is the nitrogen end. And I tell you what, we'll make that an NH3 plus. Give me another hydrogen. We'll just make that our NH3 plus end. And we're gonna, and here's the carboxyl group. Okay, now, Aaron, what has to come into this carboxyl group here? The nitrogen. So you hang on to your carbon, hang on to this carboxyl group. Bring it on in here. And we're going to split out a water molecule between these two and form an amide. That.
Romance. That's happening right now.
Water. Okay, so Stephen, hang on to that nitrogen. So that's our N-terminal end. Here's our carboxyl end. Okay, now we need a threonine. Bring up the threonine. There's only one.
I'm glad you guys are both still together. It's so awesome. It's not quite the
All right.
Now I don't know what I'm doing, so.
Okay, so we got a carboxyl group here. What does it have to react to?
I don't know.
Get in there, bring it on.
Amine.
The nitrogen. Looking at this word nitrogen. Oh, wait, I see.
Okay, go ahead, Erin, help her. Form a
Good.
peptide bond.
Take out water.
Carbon.
Another hydrogen.
Take out one of the white ones.
Just take
The
the,
white ones.
give me that. Form a peptide. And Brianna, you stay there, and Erin, you can sit down. Brianna, hang on to this carboxyl group. Okay, now we need serine. Bring up serine. And on deck is isoleucine. Isoleucine is on deck. We're getting into. So we got a carboxyl group. Bring your nitrogen in. Brianna, help her take out a water. We got an OH. Okay, what we're doing here is we are piecing together this amino acid sequence. All right, Brianna, you're all right? Come on over here, Javier. Here's your carboxyl group. All right, this is getting pretty routine here. We got a carboxyl group. Bring in your nitrogen, Javier, and break out a water. And leave a bond. And bring up cysteine, another cysteine.
All right, Steven. Here we go, dude. You ready? Just a tip.
Kind of curious over either a sheet or precious.
Yeah, but leave the bond so you can connect it. Give me that. All right. Okay, how far are we? We're right here. All right. This is all chain A. Okay, just step back just for a second. I might need your help to keep this from breaking. This is all chain A, and to get a little idea of what I mean by the secondary structure. So the primary is you've got nitrogen, carbon, carbonyl, nitrogen, carbon, carbonyl, nitrogen, carbon, carbonyl. You can see, although it isn't in a straight line, there is a thread, a continuous thread going through the protein backbone. Okay, now Dustin, hold that up real high right there. Just hold it up there. Okay, so now let's say this carbonyl, I'm going to go down 1, 2, 3, 4 amino acids, and let's say this NH group is attracted to that. Dustin was talking about how romantic this is. Okay, so let's say this NH group was attracted to that carbonyl right there. All right? And that's how you're starting to get the secondary structure. These are all within the peptide backbone. The R groups aren't getting involved yet. But there's that, and so if you came down another, if you went to this one and came down another 4, you'd have another NH attracted to that one. You'd have another NH down here attracted to this one, another NH down here attracted to this one. You see how that's happening? And this could be in a helix. I don't know if insulin is that way, but that is what we mean by secondary structure. These hydrogen bonds occurring along the backbone of the protein molecule. Okay, now while we're right here, can you hold that one right there too? Now notice here, first cysteine, 3,9 serine isoleucine, the last cysteine. We're going to form this disulfide bridge from this sulfur to this one. Okay, Dustin, go ahead and form a sulfur-sulfur bond there. All right, this is all chain A, right? This isn't the entire chain A, but everything in here right now is a part of chain A. All right? And we got this loop. I mean, off of this loop would go this part of chain A, and that part of chain A would come building off of these 2 amino acids right here. All right, now we got one more cysteine. This cysteine is this one. And it is going to bind to the second cysteine right here. Okay, so now form a sulfur-sulfur bond. So take that off. There you go. All right, so this is where chain B would begin, or would come off of chain B. And this is your parts of your insulin.
That's quaternary.
And yeah, that would be quaternary. That would be getting into the strongest part of quaternary structure. So chain A and chain B are bona fidely bound to one another, not through just a romantic attraction. A real bond right there, okay? Okay, so yeah, those are examples of this. This is a relatively small a small protein. See where to, here's insulin, 51 amino acids. So that chain A and chain B totaled 51 amino acids. Look at 104, 124, myoglobin, 153, 3 times that size. And this is one peptide chain. So all of these have primary, secondary, and tertiary structure, but not quaternary. It's only when you see 2 or more chains here that we're starting to talk about quaternary structure. Hemoglobin is about 4 times the size of myoglobin because there are 4 chains represented here. Essentially 4 myoglobins in hemoglobin.
So are residues the number of...
Yeah, residues is number of amino acids. It's just another terminology for it.
But that's not per term, right?
What do you mean by that? Not per turn.
For the first question on the homework.
That would be where I was saying you go down 4 amino acids or 3.5
Right.
amino acids, you're getting to the next,
So do we put 3.6?
the NH.
Because in the PowerPoint it says 3.6.
Yeah, that's okay because it's the carbonyl is on one end of the amino acid and the NH is on the front end of it. So you're not getting to all the way to the next carbonyl, you're just getting to the beginning of that next amino acid. The analogy I like to use right here, I mean, look at this. This protein has 4,536 amino acids in it, in a particular order. Okay? So, to kind of put you in this picture, imagine that it's you and one other person that's competing for the spelling bee, the national spelling bee. And your last word, you're given the last word, it has 4,536 letters in it. And they all have to be in the right order. Because that's what that protein is doing. It's piecing that protein together. 4,000. Remember, there's only 20 amino acids, 20 different amino acids. So it's using many of them over and over and over again. But it's using them in a right sequence, so that it gets everything right where it needs to get just the exact shape it needs so that it can function the way it needs to function. Now, I'm going to go about 5 more minutes and I'm going to let you finish your homework. But I want you to see, I want to go into this. So there's the hair. There's an individual protein in an alpha helix. And then they are wound around each other, and they come into a little unit, and those units come down into an array. And so here's the hair. So literally hundreds of protein molecules across, and they're in this alpha helix. Oh, you'll love this. Those of you that ever had a permanent. Oh, Dustin left. I was just going to ask him if he'd ever had a permanent. Those of you that ever had a permanent, what are they doing with a permanent? They're taking the hair, the natural disulfide bridges that are in the hair, they treat it with a chemical. It's a reducing agent, breaks those disulfide bridges, curl it or straighten it, whatever you want to do with it. You get it into the shape you want it, add an oxidizing agent, and what are you doing? You're reforming disulfide bridges in different places. That's why it's permanent. Till the hair grows out. Okay? But it is a permanent. So what I'm telling you is that these things fix things. It's not just an attraction, it's actually a bond. And that's how you do permanence. But what I want you to see a little bit. So here we're starting to get into hemoglobin and myoglobin. So here is a protein molecule. This is the heme. There's going to be an oxygen. So hemoglobin and myoglobin. Hemoglobin transports oxygen to the cells. Myoglobin stores oxygen in the muscles. And I want you to just see a little bit. This is the heme. You say, I've got low iron. You go to the doctor, I'm tired all the time. You know, your iron's low. Well, why do I need iron? You need iron to be in the middle of this heme. And why do you need the iron right there? Because the iron is going to hold the oxygen molecule. There's your iron. This is this heme unit. And the various amino acid residues that are around to stabilize that oxygen on the iron. This is incredible because under normal circumstances, this oxygen would want to oxidize that iron. So it has to be held there in such a way that it does not oxidize the iron, because it needs to get to the cell and do oxidation in the cell as oxygen. So that you got to hold this oxygen without it reacting to the iron. So it's very, very delicate. It just has to be perfect, because this is a very reactive molecule right here. This is oxygen. Very reactive molecule. It wants to oxidize that iron, but it's stabilized right there. So just to get a few other glances at it, there's a little bit of an alpha helix over here with an amino acid. Here's your iron, your heme complex, your oxygen sitting out here. So hemoglobin has been studied up one side and down the other side, exactly what that shape is like and how it functions. I want to use that as an example, because if you go to, you could go to 1,000 other proteins and see where that active site, and we'll do this after the exam Wednesday. Next Monday we're going to look at some enzymes and look at their active sites. That's what we're looking at with hemoglobin here. We're looking at its active site. So there's this big globular protein. Let's go back a few slides. There's this big globular protein, but here is the active site. Here's where everything happens, but it has to be in this shape for that to happen. There has to be an opening so the oxygen can get to this, and it has to just be held right there in a very critical manner. So shape of the protein is essential to its function. All right, there we go. You got 15 minutes. I would like you to finish your homework.
Hey, just let everybody know we're having a study group tomorrow at 7 o'clock. Shane Field, 1604 Starbucks. Just FYI. We got some of the classes coming from the class before.
For that bonding, for the quaternary, is it always disulfide?
No, the quaternary, but don't worry about it. It could be the hydrogen bonding. It could be different R groups, salt bridges. Yeah, it just kind of. It's not going to be a random thing, but they can use all that stuff to nestle it in right where it wants it. Okay.